In this video, we will do a quick review of equivalence relations. And I want to start with recalling the basic properties of the equals relationship. So I want to recall that with equals, we know that equals has a reflexive law, which says that A is always equal to A. And in equality, we also have a symmetric law, which says that if A is equal to B, then B has to be equal to A. And we also have a third property of equality called the transitive law. And the transitive law states if A is equal to B and B is equal to C, then A is equal to C. And these are very familiar properties of the equals relation. But it turns out that we generalize the notion of equals to what is called an equivalence relation. And an equivalence relation is any relation that has these three properties. So I want to do a formal definition. We're going to let tilde be a relation defined on some set S. And we call tilde an equivalence relation if it has, and this is a definition, so it's an if and only if and only if tilde has the following three properties. And they are exactly the same as the properties that we know that equals has. In particular, we have a reflexive property. In other words, for every element inside our set, A will be equivalent to itself. And I still don't like that equivalence, so let's make it just a little bit neater. The second property that we're going to demand is a symmetric property. In other words, if A is related to B, then B must be related to A. And the third property an equivalence relation must have is the transitive property. And the transitive property says if A is equivalent to B and B is equivalent to C, then A has to be equivalent to C. And these relations with these properties are called equivalence relations for the very basic reason that they act like the equals relation. Well, I want to actually look at some very basic, well-known examples of equivalence relations that you are very, very familiar with. So some examples of equivalence relations. The first one, of course, is the granddaddy of them all, which is the equals relationship itself, defined on any set. The second one that I want to look at and remind you of is, so from high school geometry, if we look at congruency of geometric figures, that is an equivalence relation, because if you have any triangle is going to be congruent to itself, and if triangle T is congruent to triangle S, then certainly triangle S is congruent to triangle T. And finally, if triangle T1 is congruent to triangle T2 and triangle T2 is congruent to triangle T3, then we know that triangle T1 will be congruent to triangle T3. We can relax congruency to similarity. And let me spell similarity right. Of geometric figures. That's also going to be an equivalence relationship. Because if I replace the congruency with similarity, if I know that triangle T1 is similar to triangle T2, then I know that triangle T2 is similar to triangle T1. I should have also reminded you that any triangle is similar to itself, and certainly if we know that T1 is similar to T2, and we know that triangle T2 is similar to triangle T3, then we can conclude that triangle T1 is similar to triangle T3. This is basically saying they have the same shape. The other equivalence relation that you have run into in previous math courses is congruency mod in. So our third basic example is congruency mod in. And in this one, I actually want to prove that this is an equivalence relation, just so that you have an example of how to prove something is an equivalence relation. So let's put that down as a question. Question. How to prove that congruency mod in is an equivalence relation. Well, the answer to that question is as follows. First of all, we have to recall the formal definition of congruency mod in. A is congruent to B mod in means that n divides A minus B. In other words, A minus B can be written as Q times N for some Q inside of the set of integers. Then it's just a matter of showing the three properties. So step 2 is going to be show the necessary properties. So let's see, how do we go about doing that? Well, first of all, we work on the reflexive property. So we let A be any integer, and we note that A minus A is equal to 0, and 0 is always equal to 0 times n, so n divides A minus A, and that says A is indeed congruent to A mod n. Well, then we move on to the symmetric property. And we think about letting A and B be integers with A known to be congruent to B mod n. So what I know is that A minus B is equal to Q times N for some Q inside the integers. But think about what that means. So if I multiply this particular equation here by -1, I'm going to get minus A minus B will be equal to minus Q times N. And that's going to say minus A minus a minus B is equal to minus Q times N. And that's going to say that B minus A is equal to minus Q times N. And that says N divides B minus A, so we do indeed have B is congruent to A mod n. And the symmetric property has been satisfied. And the final piece of the puzzle is to look at the transitive law. And for the transitive law, we would have to start off by assuming that A is congruent to B mod n, and B is congruent to C mod n. So what I know is that I know that A minus B is equal to something that I'm going to call Q1 times N. And I also know that B minus C is equal to something that I'm going to call Q2 minus 2, that I'm going to call Q2 times N. We need to show that N divides A minus C. So let's write that down. Need to show N divides A minus C. Well, A minus C is going to be equal to A minus B plus B minus C, and I can put parentheses there and there, but that first one is just Q1 times N, and the second thing is Q2 times N, and so we've got Q1 plus Q2 times N, and what that says is N does divide A minus C, so A is indeed congruent to C mod N, and hence congruency mod N is an equivalence relation. And that is the end of this particular video.